All right, let me just shut my door. My video should be on. Can everybody see me? Because I can't see me. There we go. Excellent. All right, let's jump in. So we finished last time talking about magnetic dipoles, and we're going to continue talking about that for a little bit, and then we're going to proceed into more in-depth on magnetic fields. So we already established what happens to a magnetic dipole when it is in a uniform magnetic field. And it's the same thing that happens for an electric dipole in a uniform electric field. In particular, it will experience a torque, and it will have some potential energy. And the formulas for the torque and the potential energy for a magnetic dipole are the same as they are for an electric dipole. However, we also know what happens to an electric dipole in a non-uniform electric field. In particular, the positive side of the electric dipole will be attracted in the direction of increasing electric field strength. And the way to think about that is that the positive side will feel a stronger force from the increasing electric field length than the negative side will, because the negative side is further away from the higher electric field strength value. And so the force on the positive side will be greater than the repelling force on the negative side, and so you get a net overall force. The same thing basically happens for magnetic dipoles. So let's go over that for a minute. So if the dipole is in a non-uniform field, we can do the same sort of analysis. So here, I'm going to draw a picture of our electric or our magnetic dipole from the side. So we have, I'm going to try to do this right. So we have current coming out the top, out of the page. We have current running down the side that we can see, and then we have current going back into the page at the bottom. So this is current that's flowing this way. And then I'm going to draw some magnetic field lines. So say the magnetic field lines look like this. Well, we know that when field lines get closer together, the field strength is larger there. And let me just quickly draw what the magnetic moment is. It's our magnetic moment mu. And so the question is, what does the magnetic dipole feel? Does it experience a force? And I mean, the answer is yes, but let's try to understand that. So first, let's look at the force on the top bit of our loop of current. So on the top bit, you have current coming out of the page, and then you have a magnetic field that's pointing to the right. And so we can use the right-hand rule that would look something like this. So current comes out of the page, out of the screen. It loops down, like the magnetic field points, something like that direction. So that's why I'm tilting my hand a little bit. And so my thumb would point mostly up and to the right. It would point mostly up, but a little bit to the right. So the force on that segment of wire would be up and to the right. Similarly, we could do the same with the bottom chunk of, with the bottom segment of the wire. So we have the wire has current coming in, and then it's curving up and to the left a little bit because the magnetic field points that way. And so we're left with a force that points down and to the right a little bit. And so the net force on the dipole is just a vector sum of the two forces on either end. So to do a vector sum, you just put the vectors head to tail. And so our net vector is a force to the right that pushes the dipole towards, that pushes the dipole in the direction of increasing magnetic field strength. In particular, it pushes the, how do I want to phrase this? Only when the dipole is aligned with the magnetic field does it push it in that direction. If it were counter-aligned, it would rotate and then be pushed in that direction. So the net force here is to the right. So we can also show this mathematically. It's relatively straightforward to show. And that's all you need is you just need to remind yourself that the force on anything in a potential field, which is what this is, there's a potential energy, so there's a potential associated with any configuration. is just the negative gradient of the potential energy. And we know that here, the potential energy of the dipole is negative mu dot B. So we need to know what the magnetic field is along the center line, but fortunately, we can assume that the magnetic field just points in the, say, x direction along the center line. Now, it might not point in the x direction away from the center line, but we only care about the center line because that's where the magnetic moment is evaluated. So in this configuration, the one that I drew above, the magnetic moment vector is just whatever, it's just its magnitude in the I hat direction. And the magnetic field along the center line is just the magnitude also in the I hat direction. So just a quick note though, B is really a function of x. The magnetic field gets larger as you go from left to right, but it still points in the same direction. And so our magnetic potential energy here is just negative mu times B. And so we can find the force in the x direction by just taking the negative partial derivative of u and evaluating, right? So this would be negative partial with respect to x of negative mu B. And so this would just be mu times dB dx. And so as long as the magnetic field, the magnitude of the magnetic field increases as it increases to the right, then you would have a force that's positive to the right? Because mu is positive, its magnitude. dB dx is positive because the magnetic field is increasing as you move rightward, so you get a positive force to the right. Right, so now before we, I would like to cover one more thing before we actually talk about magnetic fields, and that is something that you guys might actually find useful. That's the DC motors. So we all know that somehow electrical energy is converted from, or electrical energy is converted to mechanical energy somehow in power plants or whatever. The question is how do you do that? Well, no, I suppose it wouldn't be in power plants, in like motors, right? And so the way that we do that is we use rotational motion from the torque on a magnetic dipole. Yeah, power plant would be the other way around. So we know that you can put current through a loop of wire, and if that loop of wire is in a magnetic field, it will experience a torque. And so we can utilize that fact to produce rotational motion to produce rotational energy if you input electrical energy. So to do this, we need to kind of build a system. So first, we're going to need a constant magnetic field. That's how we can establish that you get a torque. So for a constant magnetic field, we just use two permanent magnets. I'm going to put this in quotes because it's not actually constant, but it's close enough. And permanent magnets are just lumps of material that happen to emit magnetic fields. And hopefully we'll get there today. But we'll explain either today or on Thursday how those lumps of material produce magnetic fields. So the picture is you have one lump of material. Let me actually draw it a little bit different. One lump of material with a north side over here and a south side over here. And then you have another lump of material. How do I copy this? Paste. Arranged in the exact same way. And so I believe this is chapter 4, somewhere in chapter 4. And so what we would find is that you would find that there are magnetic field lines that point between the two, and it's approximately constant. It's not actually constant, but it's close enough. So between these two magnets, you'll have some sort of approximately constant magnetic field. So that's good. That's how we get the constant magnetic field. Now we just need to figure out a way to establish a constantly rotating torque. So if we put a loop of current in between those two magnets, that loop of current will start to spin, right? It will experience a torque until it's arranged, or until it's aligned perfectly with the magnetic field. And it'll keep spinning because it has rotational inertia. And then it'll stop because it'll anti-align itself. And so we need to figure out a way for it to keep spinning and not just spin one way, stop, spin back, stop, and so on. Because that's what would happen if we just fed a constant current through a loop of wire. So, and we'd rather have just constant circular motion, right? That's the most useful. So instead, the way that we fix this is every time the loop makes a half turn, we flip the direction of current. So initially, imagine that my hand is the loop, right? So my hand is the loop. So current may be going around this way. It will experience a torque trying to align its magnetic field this way. And so it'll experience a torque. It'll accelerate. It'll keep moving, and then it'll slow down until it gets to here. And then if you just let it be, it would just oscillate back and forth. But if instead, once it gets to here, we flip the direction of current, so that instead of the current going this way, now it flips this way, then the dipole moment would point this way again. And so it would flip again. And so what we end up doing is that the fix is we reverse the current direction. When the loop flips halfway. And the way we do this is relatively easy. We use a device called a brush, or brushes. So the picture here, and I'm not going to draw the magnetic field. I'm just going to, well, I will, but I won't draw the magnets, is you have a loop, maybe a square loop of wire. And that current has to come from somewhere. So, it has some place that feeds the energy into it. So this is almost a complete loop. There's a little break in the loop there, but that won't significantly affect the torque. And then those two parts of the wire form like a little circle. And the circles are made out of metal. And then you have other circles other semicircles made of metal. Like this, that are attached to your battery. And so those circles of metal, these are the brushes, these green things. And so the point is that you have I'll just drop my pen. Initially, you'll have current flowing this way. But then half a rotation later, because it will experience a magnetic field to rotate, the brushes will flip direction. And so this side will be the one that's connected to the positive side because the circle will rotate. And so then the current will again be oriented this way. So using this configuration of brushes, you can basically have a slipping contact between your current source and the actual loop so that the direction of the current changes sign every half turn. And it's a really clever invention, and it's how you can make very small electric motors that constantly have that are constantly experiencing torque. So would brushless motors be more efficient than it? So the brushes are green. Sorry, let me label it. Let me write it in green. And just think of them as like metallic brushes. Like they're literally like flexible pieces of metal that contact the thing that they're pushed up against. And so Henry asked about brushless motors being more efficient. I'm actually not sure if they're more efficient. I don't have a good understanding of how brushless motors work. I'd have to think on that, but I don't know the answer. The brush is the part attached to the circuit or the loop of the current? Yeah, they're the part attached to the circuit. The loop of the current would be what the things that the brushes are touching. But hopefully you guys can see why this works. So initially, when the torque is initially, like in the configuration described here, you have your moment vector pointing up and you have your magnetic field pointing to the right. And so in that case, at t equals 0, the torque is maximized and it will cause it to rotate clockwise. At say, yeah, the brushes are stationary. After a quarter of a turn, the magnetic field would be aligned with the magnetic dipole moment would be aligned with the magnetic field. They lose, I mean, like this is a mechanical thing, so you can make it so they lose contact for as minimal amount of time as possible. That would be fine though, because you don't need any current at the perpendicular point. The torque is 0 anyway, so you don't need any current. But anyway, so at a quarter of a turn, the torque is 0, but it's still spinning because it has inertia. Then it'll get to half a turn, and if there were no brushes, it would just slow down because the torque is in the opposite direction, and it would flip and it would experience a torque in the opposite direction and then flip back the original way. But because the torque is because there are brushes, it'll slow down until it gets to here, and then it'll experience a torque again and speed back up. So you'll get constant motion. And for more uniform type of circular motion rather than like motion that's kind of jittery, you can have more brushes and you can have more contacts and things like that. And you know, those are all engineering problems, but in principle, this is how a brushless motor works. Right. So that's the basic gist of an electric motor. Everything else is an engineering problem, and that's your guys' job, not mine. So at this point, my job is done, and I'm going to change topics, and we're going to talk about magnets again. So we really want to be able to answer the question, how do magnets affect each other? So you guys should know probably from common experience that if you have two magnets, if you put the two magnets in one configuration, they'll like stick together. And if you flip one of them, they'll repel each other, right? Just think like if you have a little cube magnet or a little circular magnet or whatever, fridge magnet. Don't worry, we will talk about what even is a magnet later. And so if you think about this enough, that flipping one of the objects in your configuration changes the direction of the force, you might even realize that this is similar behavior to what you would experience or to what you would expect from an electric dipole. So if you consider an electric dipole configuration, so let's say you have an electric dipole with a minus and a positive charge here, and we know what the, actually let's, yeah, no, that's fine. You know that the electric field lines will go like this. Something like this, right? So if you take another electric dipole and you put it next to it, come on, paste, will you? Stop opening up the keyboard. Well, let's think about what force. Let's imagine that this one is fixed and this one is free to move. So let's not imagine what the electric field produced by this dipole is. Let's just draw the dipole and imagine what force it's on, because the electric field that this dipole produces won't affect the other dipole because the other one is fixed in place. So we just have a dipole here. Now, the electric field from a dipole decreases as 1 over r as you get further away. So the magnitude of the electric field here is smaller than it is over on the left-hand side. And so we know that electric dipoles feel a force in the direction of increasing electric field. Sorry, that should be large, not small. And it kind of makes sense, right? The negative charge is closer to the positive charge than the positive charge is. So the net force overall would be to the left in this case from the other dipole. So the two dipoles are going to attract each other, and that's because the positive side is closer to the negative side. And similarly, if we were to flip it, if we were to put the negative side on the right and the positive side on the left for the rightmost one, if we were to flip this one, then it would feel a repulsive force because the positive side is closer to the positive charge than the negative side is. So this is just another way that you can get two things that attract each other if one of them is in one configuration and repel each other if one of them is in the other configuration. So clearly there's, or at least hopefully clearly, there's some sort of similarity between these two things. And it turns out that it's precisely this type of behavior that magnetic dipoles also have. So we can draw a magnetic dipole. Magnetic dipole might look like a loop of wire. With current going this way. The magnetic dipole moment would point in the to the right. And we would find that the, actually, before I do that, let me just say, because we'll get to that later. Let's say that we just have a magnetic dipole. It will have magnetic field lines that come out in one direction and come in on the other direction. And so if you were to put another dipole over here, say that this one is fixed and this one is free, well, depending on which way the fields align, if this dipole is arranged so that it has fields coming in on this side, it will feel the same sort of attractive force. Because remember, if we were to draw the field lines for the electric dipole up here, it would have field lines coming in this way too. So in this arrangement, this would be attractive. In the opposite arrangement, so we're keeping the left one fixed. But we're flipping the right one. Now we would get a repulsive force. And that's precisely because the fields would be arranged in the same way for the electric dipole. And this just boils down to the fact that if you have a field from, say, the fixed dipole, the magnitude increases or decreases depending on which direction you move in. And so a dipole, as we established up here, a dipole will feel a force that points in a direction that, the dipole will feel a force that moves in the direction of increasing magnetic field. So this is all to say that we can label, just like how there's a positive and negative side for an electric dipole, we can label a positive and negative side for a magnetic dipole. We label the side that has magnetic fields coming out as the north side, the north pole. We label the side that has magnetic fields coming in as the south pole. And so here, this probably agrees with what you learned in grade school. We're always flipping the free one. The fixed one is just fixed. In grade school, you learned that the north pole attracts the south pole and the south pole attracts the north pole. And if you have two like poles, they repel. Two different poles, they attract. So just to put this in words, the end of the magnetic dipole. Oh no, you didn't know about this until now? Okay, well now you know. They don't teach this in like middle school science? Sorry, I just had to write this out so you guys have something to reference. Right. So the North Pole, so yeah, you guys learned what I meant to say is that you guys learned that south attracts north and north repels north, but you might not have learned why, how you can characterize a north as opposed to a south pole by looking at the magnetic field. That's probably not something you learned. But the basic gist is that because the field gets weaker away from the dipole, the north pole of a magnet, which is the direction, so draw a magnet here, you have a north pole and a south pole. So the magnetic field lines get weaker as you get further away, right? Because they're spreading out. And so if you have a dipole that's arranged this way, then the direction that the arrow is pointing, the direction of the magnetic dipole moment, is pointing the direction of increasing magnetic field. So there would be a net force this way. And so this kind of dipole is one that has its north face on the left, or its north side on the left. That's why this happens. So now here's where things start to get weird. So in an electric dipole, it's just a positive and a negative charge that are near each other, right? And they're fixed, some fixed distance. So you can just cut the dipole in half and you end up with a positive charge on one side and a negative charge on the other side. No, importantly, we're not going to refer to positive or negative side. North and south is the language that we use for a good reason. So the question is can we chop a magnet in half? Can we chop a dipole in half to get a north and south charge? Yeah, and as everybody is saying in chat, the answer is no. Maybe you don't know why. I don't really know why either. Well, I kind of do know why, but it's a harder question than you might suggest. So just with everyday pieces of metal that are magnets, so every time you cut a magnet in half, and when I say a magnet, here I'm referring to permanent magnets, lumps of metal that are magnetic. Every time you cut a magnet in half, you just end up with two smaller magnets. Both of which have the north and a south side. Yeah, you could put them back together. In fact, they will attract each other and they'll want to go back together. So maybe we can understand why this happens by just looking closely at the fields for a dipole, for an electric dipole and a magnetic dipole. So for an electric dipole, something in my mouth, cat hair, I think. So for an electric dipole, we have a charge and a charge. Let me give myself a little bit more room. And this is going to be a terrible drawing, so for that I apologize. And we might have a field that looks something like this. God, these are always so hard to draw. Right, so that's what our electric dipole looks like. And so if you look at a magnetic dipole, I'm not going to draw 2 points because that's not how it's represented. I'm just going to draw a field. And if we want to see what a magnetic dipole looks like, we can just look at like a loop of charge running in a circle. The field lines instead look like this. They don't change direction in the middle. So on the outside, they look basically the same. You have field lines coming in on one side and going out on the other side, and you have these loops, these loops of magnetic field on the top and bottom. But there's no difference between one side of a dipole and the other. Like if you were to cut this in half, you would still just have electric fields. You would still just have fields that go from left to right, regardless. Whereas if you cut this one in half, you have one side has fields that go out and another side that has fields that go in. So the difference is in the structure of the fields. Magnetic fields just, they're always pointing from left to right. Maybe I shouldn't have drawn those loops up there, just to be a little bit more clear. They're always going from left to right. If you don't, so I mean, like, are you just saying if you have a block of magnet and then you just put like a cut in it, like that, then I mean, you'll just have field lines that pass through the air. You can try to come up with whatever you want, but there's no way to actually get magnetic to separate out a positive from, or the north or from the south poles. Not possible. So the conclusion here, and by the way, there's a better picture of what's happening here in section 4.3. So the conclusion from this noticeable difference between electric and magnetic dipoles is that magnetic field lines always form closed loops. And so that's why I initially drew circles, because they will close back in on themselves, but sometimes it's very far away. Whereas electric field lines start and end on charges. So this is an important observation, right? There's no place where the magnetic field lines start. They're just always going. And if you look far enough away, they'll close back in on themselves just really, really far away. So yes, Carlos, and we will get to that. So it turns out that like this notion of magnetic monopoles, i.e. like magnetic charges, just like how there are electric charges, as far as we know, none of them exist in the universe. Like they just don't exist. There's no reason to think that they couldn't have existed. Like if we restarted our universe and gave it a different set of physical laws or a different set of conditions, maybe you could have had magnetic fields or magnetic charges, but they just don't seem to exist in our universe. And so what we do is we just formulate our equations, our laws of physics, to in a way that agrees with that. And so while we're not entirely sure that they don't exist in our universe, like you can't prove a negative, so we haven't found any, but we could have just missed them. For the purposes of this course, we're going to assume that there are no magnetic charges. They just don't exist. And so from this conclusion, we can actually come up with the Gauss's law for magnetism, which is really nice. So any magnetic field line, if you have some surface, he comes up all the time. If you have some closed surface, think Gaussian surface, any field line that comes in or goes out can't stop inside the surface, right? Because the field lines never end, they just close in on themselves. So if you have a field line that comes into a surface, let's say your surface is like this weird lump of bread thing. If you have a field line that comes in, it'll come out somewhere. And so the point is that the net flux through any closed surface, the magnetic flux, sorry, through any closed surface is 0. And the only reason it's not 0 for the electric case is because you can have field lines that just appear out of nowhere. So if you have a charge inside your surface, those field lines will all be pointing out or all be pointing in. And so they just kind of spontaneously appear. They don't have to enter and exit. They just go out or they just come in. For magnetic fields, they can't just start or end somewhere because there are no magnetic charges. So they always have to go out if they come in. And so mathematically, that would be that we write that the magnetic flux, so this is just the flux symbol, phi, with the subscript B for magnetic field, that this is 0. And so we can then write the magnetic Gauss's law, which is that, so it's just the formula for flux equals 0. So we get that the integral of B dot dA equals 0. That is the integral form of Gauss's law for magnetism, or equivalently, that the dot product, sorry, the divergence of the magnetic field is 0. So this is Gauss's law for magnetism. And this is really just a rehashing of the statement that there are no magnetic charges. If there were magnetic charges, there would be stuff on the right-hand side here. But because there are no magnetic charges, there's no stuff on the right-hand side. That's all. Right. So, hey, I might, who knows? It's a good type of question. It makes you really think, right? So that tells us about what magnetic field lines do, but it doesn't tell us where the magnetic field lines come from. So we know that the magnetic field lines can't come from magnetic charge. That's what we've established here. It just doesn't seem to happen in our universe. So where do they come from? Well, they do come from a type of charge, just not the kind that you might be thinking. So let's talk about the field. I should probably give this a letter. So the B field, magnetic field of a moving charge. So when we first started talking about magnetism, we established that in order to have a force between two lines of charge, just like how there's electric charge, well, so when there's electric charge, you have stuff on the right-hand side of the Gauss's law. Gauss's law for electric flux tells you that the flux is related to the amount of electric charge contained within the surface. Because there is no such thing as magnetic charge, there's nothing on the right-hand side of this equation. The field lines don't stop and end on some sort of magnetic charge because magnetic charges don't exist. That's what I mean. Right. So we established before that if you have two wires that are both have a current flowing through them, they'll experience a force between them, either attractive or repulsive. And so the question is what about those wires makes them experience a force? And we kind of established that it has to be the fact that there are charges moving in both of the wires, because if one of them didn't have current, then there would be no force between either of them. So there has to be movement of charge in both of those wires. So we can just kind of simplify down even further and just ask, well, if the force on one of the wires is due to the magnetic field from the other wire, that's how magnetic force is conveyed. It's conveyed through the magnetic field. Then that means that moving charges in one of the wires produces a magnetic field. And so what we have is if you have a whole bunch of charges that are moving in the same direction, you'll get a big magnetic field. And so the question is how much magnetic field does a single charge make, a single moving charge make? And by the way, for the remainder of this, or not for the remainder, but from context, whenever I say charge, typically I will be referring to electric charge in the traditional sense. And so if a charge is just moving through space, it will produce some sort of magnetic field, because all it takes is a whole bunch of charges to make a current, right? A whole bunch of charges moving in the same direction. So a single charge should produce a little magnetic field. And indeed, that's just true. So it just is the case that moving charges produce magnetic fields. So when we were initially talking about the electric field, if we wanted to figure out the electric field at a point from some point charge, there was only really one vector in town that could produce that electric field. There was the vector that pointed from the point charge to the place of interest. For magnetic fields, there are two vectors in town. There's the vector that points from the moving charge to the point of interest, and there's the vector that points in the direction, or there's the velocity vector of the moving charge. So it turns out that to produce the magnetic field, it should involve both of those vectors. The displacement vector r and the velocity vector v of the moving charge should be involved. And so you might already be able to guess what form this magnetic field has to have. There's only one way that you can produce another vector, i.e. the magnetic field vector, given two initial vectors. Well, I guess there's a few ways. You could just add them, but they don't have the same units, so adding them doesn't make sense. The only way that does make sense, that's consistent with units, is to cross them. Take the cross product of two vectors and you get a third vector out. So you could probably already guess that we're going to have to take the cross product of the velocity vector and the displacement vector to get the magnetic field, and you'd be right. So let's work through that. So the Biot-Savart law is, again, it has the name law, so it was derived empirically by doing experiments, established what the relationship is between a moving charge and the magnetic field it produces. So one of the relationships, it's a proportionality, is that the magnitude of the magnetic field produced is proportional to the magnitude of the charge. And so this is just like the Coulomb law. We saw that if you have more charge, you have more electric field. Similarly, if you have more moving charge, you have more magnetic field. Another result that's easily viewable from an experiment is that the magnitude of the magnetic field is proportional to the magnitude of the velocity of the moving charge. And this should be relatively straightforward. We know that if the velocity is 0, it doesn't produce a magnetic field, thinking back to the current running through a wire experiment. So the magnetic field should be proportional to the velocity, because if the velocity is 0, the magnetic field should be 0. Another relationship that we find just by doing experiments, moving charges, seeing what happens, would be that the magnetic field is proportional to the distance, or is inversely proportional to the distance squared. This is just like the Coulomb law, which just says that the electric field goes as 1 over r squared. The magnetic field also goes as 1 over r squared. If you double the distance from the moving charge, then you then you quarter the magnetic field strength. These are all, hopefully you can see where all of these, how these could all be experimentally determined. You shoot an electron in a direction, you measure the magnetic field somewhere, and you correlate them just by plotting data, right? And you would find these correlations. Finally, this one's a little bit weird. The magnetic field is parallel to V cross R. So, like I was saying earlier, both the displacement vector, remember R is the vector from, it's because they mean the same thing. The magnitude is just a generalization of absolute value. Right, so because we have to incorporate both a velocity and a displacement vector, the only way to produce a third vector out is by taking the cross product. So the end result from all of these proportionalities that you determine from experiment is that the magnetic field is proportional to all of these things. And in particular, there is some constant of proportionality, which we call mu naught over 4 pi times q v cross r divided by r cubed, and I'll explain that in a minute. And this is what the magnetic field is. The stuff out front is just a constant of proportionality. We see that if you increase the magnitude of q, you increase the magnetic field. If you increase the magnitude of v, you also increase the magnetic field. If you move away from the source, from the moving point charge, then you decrease the magnetic field. And so this agrees with the established proportionalities above. This is known as the Biot-Savart law for moving charges. Now I did say, right, good question. So that r cubed comes from the fact that we want the vector to point in the same direction as v cross r, but we don't want to be using v cross r hat. We don't want to use, so instead what we do is we just write that r hat is equal to the vector r divided by its magnitude. So sometimes you'll see this written equivalently as mu naught over 4 pi times q v cross r hat divided by r squared. And then you can see that really it is just the distance squared that it's related to. And so sometimes one is more useful than the other, so we'll interchange. But this is just a way of reading these things. Now, we need to know what this constant is. if we want to do calculations. So let me tell you what it is. So mu naught is the permeability of free space. So it's not permittivity, it's permeability. Sorry that the names are very similar. And it has value exactly equal to 4 times pi times 10 to the minus 7 Tesla meters per ampere. So there's a reason why this constant has the value it does. It is exactly 4 pi. It's not just approximately, and so we say it is by definition 4 pi times 10 to the minus 7th. And so you might say, well, why do we have this mu naught over 4 pi at all? Well, there are good reasons for it. And basically it's because we want that, we want mu naught to basically play the same role in magnetism as epsilon naught plays for electricity. And so there has to be this built-in 4 pi. That's why it has the formula it does. But we'll talk about that in more detail later. So with this formula, we can then figure out what the magnetic field is for a single moving charge. So let's say that we have a charge, call it plus q. It is moving to the right with velocity vector v. So let's say that we're interested in the point over here. Let's call it a blue point. Let's say we want to know the magnetic field there from that moving charge. Well, we would need to find the displacement vector, r, and then we would need to cross it with the velocity vector, or cross the velocity vector with the displacement vector. And so what you would find is that the velocity vector there, if this was in 3D, it would be easier to indicate. The magnetic field at that point would point something like into the page. And so I'm going to do my best to draw what this would look like. So the magnetic field takes the shape of a ring that's symmetric about the axis formed by the velocity vector. So here, this is, to be more precise, this would be into the page. Let me make sure that that's right. No, sorry, that should be out of the page. Let me just reverse these arrows. Oh no. Okay, well, I'll just redraw it. So here you would have, I actually didn't need to reverse that at all. I could just change the perspective, right? So here you have magnetic field coming out of the page. Here you would have magnetic field coming into the page. And then here you would have magnetic field pointing down. And here you'd have magnetic field pointing up. So it's hard to draw because it has to be three-dimensional. But basically what you end up with is you get a circle that is centered. So the magnetic field some distance away from the moving charge is a circle centered on the line formed by the velocity vector. And the value of the magnetic field is the same everywhere on that circle, but it just changes direction. So there's actually a relatively easy way that we can then use the right-hand rule to get a gauge as to what direction the magnetic field circulates in. So here, and we'll use this language a lot, the magnetic field here circulates in a direction. In this case, it circulates into and out of the board as described. So let me just put this in words. So we can use the right-hand rule to determine that direction. So you stick your thumb in the direction of the velocity, and then the fingers curl in the direction of B. And obviously that's only true for positive charges, right? For negative charges, the sign is different. But so if the vector is pointing to the velocity vector points to the right, then at any point, like if I were to find say the magnetic field, say here, above the line, which is this point is, the magnetic field comes out of the page. Below the line, the magnetic field comes into the page. To the side of the line, the magnetic field comes downwards. That would be like to the left of the charge if you were viewing it from behind, and to the right of the charge, it would be coming upwards. So you can use this to just figure out how the magnetic field circulates around a moving charge. And that will apply for currents as well. If you have current flowing in a direction, your hand rotates in the direction that forms the magnetic field. So let's talk about current carrying wires. So we established before, I think it was last week, that you can rewrite current. You can rewrite the current times the path length that the current is traveling through in terms of a small amount of charge times the velocity vector. And so we can just use that to just directly substitute in to the Biot-Savart law for a single moving charge, and then we can integrate. That is, the magnetic field is an integral of dB, which would just be an integral of mu naught over 4 pi times I over r squared dl cross r hat. I need an open bracket there. By the way, here I was using this formula. I was using the r hat over r squared term rather than r over r cubed. Just keep that in mind. And so depending on, like, if this was an infinitely long wire carrying current, then you would have to parameterize L. You would have to figure out what R is. You'd have to end up doing an integral from, say, negative infinity to infinity. But at the end of the day, it's just an integral. You're just adding up the magnetic field contribution from each small chunk of current carrying wire. So let's do that for a long straight wire. So infinitely long straight wire. And by the way, you are going to find that in general, finding magnetic fields is a lot harder than finding electric fields because there's a curl involved, not a curl, say a cross product involved. It's going to get nasty. So that's just a warning. I'm going to say that the current through it is I. God, my nose is so itchy. I'm sorry. So this case is really simple. So it's relatively similar to the equivalent case for an infinite line of charge, but you're going to see that it does get complicated quickly. So we're going to find Spain. We're going to find the current. We're going to just do a tiny chunk of charge. A tiny chunk of current moving upwards, has path length vector dl, which has length, whatever its length is, and it has points upwards, points in the direction of current. I'm going to give an x-axis here, say a y-axis going upwards. So let's call this position y. And let's say that we're interested in what the magnetic field is at that point. So we're going to need to figure out this distance, call it little r. That's the square root of y squared plus capital R squared, where this distance here is r. Sorry, I should have made that clear. And the vector the vector r hat points this way, right? And that's just the vector r hat from just that single chunk of current. By the way, we're going to be referring to these as like little segments of current or chunks of current, just like how we referred to charges as chunks of charges when we were talking about infinitesimal chunks. So now let's just do the vector calculations directly. So dl, in this case, we want to parameterize it in terms of the coordinate variable y. So this is just dy in the j hat direction. Now, what about the r hat vector? Well, the r hat vector almost points straight, almost like if the vector was like this vector, it would just be cosine plus sine, cosine I plus sine j, right? But it's pointing down, so this is just cosine theta I minus sine theta j, where this angle here is theta. So we can figure out what that cosine is. So the cosine of theta, in this case, is just r times square root y squared plus r squared, right? We could figure out what sine is. It would be y, the sine of theta would be y over square root y squared plus r squared. Turns out we won't need it. Oh, and by the way, this direction here, that's the z direction. We needed to have a right-headed coordinate system. So now we can compute dB, the small contribution of magnetic field from that chunk of current. Well, actually, let's not do that yet. So to compute dB, we're going to need to know what dl cross r hat is. We're going to need that, so let's just do it. So dl, we already know what that is. That's just dy times j hat, and we want to cross it with the vector r hat. Cosine of theta I hat minus sine of theta j hat. So j hat cross j hat is 0, so we can drop that term. So this works out to be cosine of theta times dy, and then j cross I is minus k. So this is minus k hat. Cosine of theta we've already established is r divided by the square root, so it's just r over square root y squared plus r squared. dy, put a negative sign there and a k hat here. So that's dl cross r. Okay, so far so good, not so hard. Now we can just compute dB. And that we can do directly. There's no more vector calculus to be done. dB is mu naught over 4 pi times I dl cross r hat divided by r squared. And we already know what dl cross r hat is. So this is mu naught times 4 pi. I'm going to factor out the constants. Or not factor out the constants, but I'm going to factor out the everything that's not dl cross r hat, sorry. So r squared is just y squared plus r squared. Little r squared is y squared plus big R squared. We multiply it by dl cross r hat. So this term here, minus r divided by square root y squared plus r squared dy k hat. All right, so that's what our dB is. We can simplify this a little bit. We get that it's minus mu naught IR over 4 pi times dy over r squared plus y squared to the 3/2 in the k hat direction. All right, that's what our dB is. And now all we have to do is we have to add up all of the chunks of current from infinitely far down to infinitely far up. It's an integral of dB, which is just negative mu naught IR over 4 pi times the integral from negative infinity to infinity dy over r squared plus y squared to the 3/2. It's not that it goes to 0, it's that the cross product of j with itself goes to 0. And the sign is the coefficient of j, of that cross product, k hat. And now this is just an integral to do. So we've done this type of integral a lot. This ends up being 2 divided by capital R squared. And so our magnetic field ends up being negative mu naught I over 2 pi r k hat. So if I were to draw this picture, let's do a better picture, with current running up, then the magnetic field, well, so on the right of this, on the right of the wire, the magnetic field points in the negative k direction. So here we would have a magnetic field that points into the page here. If we were to do the same thing on the left, we would find that it points out of the page. And so what we find is we find the magnetic field circulates around the wire this way. And the magnitude is mu naught I over 2 pi r, which is really very similar to what you should have found for an infinite line of charge, right? The answer is basically the same. They both go as 1 over r. They both have a factor of 2 relative to what the typical bios of r is, because for a line charge, it's lambda over 2 pi epsilon naught r. So here it's mu naught over 2 pi. And then we have I over r instead of lambda over r. So it's really very similar. And just as a quick aside, if there are multiple wires, if we had like a whole bunch of infinite wires that were all near each other in space, we can just use superposition of the magnetic field. So I didn't actually explicitly get the direction of circulation. What I established is that the magnetic field to the right of the wire is into the page. And you could have done this exact same calculation to the left of the wire, and you would have found that it's out of the page. If you had done it over here, it would have pointed in the positive k direction. And then if you had done it, say, back here, you would have found it pointed to the left. And if you had done it out front, you would have seen it pointed to the right. And so you can establish that it does just go around in a circle. And it really ought to, because it's the system is cylindrically symmetric. So it has to go in a direction. Right, so if there are multiple wires, you can just add up the magnetic fields from a bunch of those wires to find the total magnetic field. The only thing you have to be careful about is that the directions for the magnetic fields point every which way, right? They go in a circle. So you'd have to be very careful about what direction those magnetic field lines point in before you add them together. We got k hat because we did a cross product between I and j, and we got the negative direction because it was the cross product of j. It was j cross I. Go away. There we go. It went away. Right. Okay, great. So that is the infinite wire with current running through it. There are some examples of this, by the way, that you can see. I linked them in the lecture notes, so you'll see those after I post the lecture notes. The next example to work through is the magnetic field, and this will probably be the last thing we do today. The magnetic field from a loop of current. So typically, we're not going to work with an infinite wire because there's no such thing as an infinite wire, and where would the current come from? But we will often work with loops of current that is just going in a circle. So let's figure out the magnetic field from that. So this is going to be harder. It's definitely messier. And I outlined this calculation in the lecture notes, so if you want to take a look, go ahead. So here's the picture. So we have our loop of current. Let me draw it. It's especially hard because I have to draw it in 3D. So here we're going to have, actually, let me do this, just so you can see what direction it's in. Oops. So here we have our center. Imagine that these are indeed solid, but it's hopefully now you can see that it's a little bit more 3D. So we have our loop of wire. This is behind, we have current flowing, say, this way. So it comes from the back, or comes from the back, comes towards you, goes back towards, and so on. So here is the front, here is the back, just so you guys can get a perspective, because I know it's kind of hard to view. And so say we want to know what the magnetic field is along the center line at some position, say 0, 0, z. So here we have our x-axis, here we have our y-axis, and then here we have our z-axis, standard coordinate system. So we need to add up the magnetic field contribution from all of the little chunks of current that go around our loop, right? So this chunk of current that I just drew has magnitude, or it has current I running through it, but it has length dl, and we need to use that vector dl. And that, I'm going to try it. This is so hard to draw. That chunk of current has a vector that tells us where it is from the origin. Let's call that the vector r. And by the way, the radius of our loop is also r. So that vector just tells us the direction, and the magnitude is capital R. Then we have another vector that points from that chunk of current to the place of interest. that's our vector little r. Let me actually make it solid. That vector is little r. So that's the vector that we're going to use as little r in our calculation of dl cross r, right? Finally, we need to give some sort of angle to this, because this is going to be a polar integral. So that angle there, we're going to call phi. And I know this is getting really, really cluttered. So here the loop lies in the xy plane. All right, hopefully everything is set up. So the angle that the small chunk of charge makes with the x-axis, or the angle that the vector r makes with the x-axis, is phi, lowercase phi. The vector r points from the origin of our system to our small chunk of charge. The vector little r points from our small chunk of charge to the point of interest, which is along the z-axis. All right, that's all the preliminary geometry that we need to do. So we're going to just do some calculations now. So first, let's make an observation that will help us in the future. So this sum, the vector sum of the vectors big R and little r, that should be equal to the vector z in the k hat direction. And the reason for that is because you can just stack vectors end on end, and that gives you a sum, right? Like that is a vector sum. So if you stick little r on the end of capital R, you get a vector that points from the origin to the point of interest, which is the vector z in the k hat direction. So what that tells us then is that the vector r is just negative big R plus zk hat, which is a really useful relationship because it'll give us it's kind of a cheat code as to what R is, so we don't have to calculate it. And as just a quick note, the magnitude of R is the square root of capital R squared plus z squared. That's just the Pythagorean theorem. You have one leg has length capital R, one leg has length z. So the length of that vector of the hypotenuse is r square root of r squared plus z squared. Second, another observation is that the length of dl, the magnitude, it's just the standard polar coordinate length. It's just r times d phi. So if it extends a little bit, if the angular extension is d phi, multiply the angle that it extends over by the radius, and you get the arc length. Also going to be a useful equation. How are we doing on time? Not well. I might run a few minutes over so I can finish this calculation because it's a good calculation. Well, we'll see. So before we continue, I'm just going to be explicit here. We need to find dB and integrate. So we can write out what the formula is for dB. So dB, small chunk of the small amount of magnetic field contribution from that small chunk of charge at the point of interest. Well, it's mu naught over 4 pi times I dl cross r hat. Actually, I'm going to use r vector divided by r cubed. Okay, so we need to compute dl cross r. Well, so dl cross r is dl cross, well, we have a formula for r, right? For little r. It's negative big R plus z in the k hat direction. And so we can expand this. We get that it's r cross dl. Remember, when you flip the order of cross products, you get a negative sign, plus dl cross zk hat. So now we can just figure out what these are. So we know the length of dl. We know the length of r. We know the length of zk hat. So we know all the lengths. We just need to figure out the directions. So from the picture, the r hat crossed into the dl vector, r hat is in the xy plane, as is the dl vector. They're both in the xy plane. So the cross product has to be in the z-axis, has to be in the z direction. And that's just from the geometry of the picture. So we know that r is perpendicular. Oh, and they're also perpendicular to each other, right? They're at right angles. R is perpendicular to DL. So R cross DL is parallel to the k hat direction. And then we can do the same for DL and Z, or NZK. So DL is in the XY plane. ZK hat is along the Z axis. So we have that DL is also perpendicular to k hat. So we get that that DL cross k hat is also parallel to R hat. So basically there are three vectors here. There's R, there's DL, and there's ZK hat. And those form a mutually orthogonal set of coordinates. So the cross product of any two will give you the third. And then you can just use the right-hand rule to determine whether it's in the positive third or the negative third. And so what we find from those observations is that DL cross R is R times DL k hat. That's the first term. So it's just the product of their magnitudes in the direction that we established, plus Z DL R hat, where R hat is the unit vector that points in the same direction as the R vector. And so we can just expand this. We know that DL is R d phi. So this is R squared d phi in the k hat direction, plus ZR d phi. And then what is the unit vector in the R hat direction? Well, it's just cosine of phi plus sine of phi. It's just the standard one in the I and j hat directions, respectively. So putting this all together, we get that B, the magnetic field at position 0, 0, z, from this loop of wire, it's going to be an integral from 0 to 2 pi. So I'm going to factor out I, I'm going to factor out as much as I can. We get mu naught times I over 4 pi. So that's the only stuff that's not constant. Times an integral from 0 to 2 pi. We're integrating all of the angles around the loop. So we have d phi. So they all have a d phi in them, right? So I'm just going to factor that out. And then we have divided by r cubed. So that's going to go on the denominator here. R cubed is r hat plus, or r squared plus z squared to the 3 halves. And then we have all of the stuff left over. So we have z r cosine of phi in the I hat direction. That's this term here. Plus z r sine of phi in the j hat direction. That's this term here. Plus r squared k hat, which is this term over here. Now, you guys know what so we're doing an integral over phi here. So an integral over phi means the only terms that vary with angle are cosine of phi and sine of phi. So we can just do that integral. The integral of cosine of phi is sine of phi. And if you evaluate sine from 0 to 2 pi, you get 0. Similarly, the integral of sine of phi from 0 to 2 pi is also 0. So both these terms die in the integral. And so what we're left with is that the magnetic field at position 0, 0, z from this loop of wire is mu naught I r squared divided by 2 times r squared plus z squared to the 3 halves in the k hat direction. That is our answer. It's a long calculation, but it gets us a good answer. They die because the integral of sine theta d phi from 0 to 2 pi is 0. And the same is true for cosine. How are we on time? Oh, we're just about done. So then we can apply this formula to figure out the magnetic field at the center of the loop. At the center of the loop, z is equal to 0. And then we can use this formula. So that implies that the magnetic field at the center of a loop simplifies a lot. It's just mu naught I over 2r. Now, you might go back and realize that that's basically the same formula for as it was for a line of current. And there's a sort of duality here. If you have a magnetic field, you can kind of swap a magnetic field with a current. Like if you replace a magnetic field with a current in all directions, you kind of get a duality between the magnetic fields. There's an interesting relationship there, and I encourage you to think about it. But just before we continue, or before we end for the day, from this relationship, we've established Oh, by the way, the end result is that it points out of the page. So the magnetic field points this way, points in the z direction, in the plus k hat direction rather, right? So, and if you were to do this for, sorry, it points in the plus z direction. It's not out of the page, it points to the right. So another shortcut that we learned from that example, another right-hand rule shortcut, is you curl your fingers in the direction of the current. And your thumb points in the direction of the magnetic field. So we can try that here. So it's coming out of the page. So the current's going, sorry, out of the page. So the current's going this way, and the magnetic field to the right, or the magnetic field points to the right. And indeed, that's true. So it's a nice nifty shortcut. You can use your right-hand rule to just figure out what direction magnetic fields point depending on what current you have. So I will leave it there. We'll continue with more on Thursday.